All right, so in our first couple videos, we talked about what ionization energy is and what that chemical equation looks like. And then we also talked about when you take one electron away and then two and then three and then four, how that ionization energy increases, especially as you go from the valence electrons to the inner shell electrons, where you do see that big jump. Okay, now what we're going to do is we're going to talk about our good friend, the periodic table, okay, and how the ionization energy of an element changes as you move around the periodic table. So we're going to talk about two different patterns we're going to find today. So let's say we've got our periodic table here, and one pattern we're going to talk about is when you go across the periodic table. And the other pattern is going to be what happens to ionization energy as you go down the periodic table. So, as you move around the periodic table, and again, now remember yesterday, in our previous video, we talked about the first ionization energy, the second, the third, the fourth, the fifth, etc. Now, when we're talking about patterns on the periodic table, when we're looking at these patterns, we're only talking about the first ionization energy. We're only talking about taking away that first electron. Okay, so let's look at the table here, and we can kind of see this. So let's talk about, let's see, what do I talk about first? From left to right. So let's start from hydrogen to helium, you're going left to right. As you're going from lithium over to neon, you're going left to right. As you're going from sodium to argon, you're going left to right. What do you notice? Notice over here the ionization energy. What happens to that first ionization energy as you go from left to right? What is the general trend? And that's all we're looking for here. What's the general trend? Well, clearly, what are all these arrows doing? They're going up, 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 up. As you go across the periodic table, the ionization energy goes up. Now here, this is the D subshell. We're not going to talk about the D subshell. Clearly, not much of a real pattern there. Okay, there are a couple of drops here. We're not even too worried about those. We do discuss those in AP, but don't worry about those. Okay, all that we're worried about is the general trend is as you go from left to right, as you do this right here, as you start from the left-hand side and go to the right-hand side, the ionization energy goes up. So that means that elements that are on this side of the periodic table have higher ionization energies than elements on the left side of the table. Okay, because as you go across, the ionization energy goes up. Okay? So, let's talk about why. Okay? Oops, I erased my periodic table there. Okay, so there's my beautiful, oh geez, I don't know what that is there, sorry. Periodic table there. As you go across the periodic table, let's say you're starting, here's period 1, here's period 2. So we're starting here at lithium, and we're going to neon. So here's Li, and you're going over to Ne. And we can see that, again, the ionization energy is going up. Why is it going up? One of the reasons is, as you go across the periodic table this way, what's happening to the number of protons? Well, certainly the number of protons are increasing. Okay, lithium has 3. Beryllium has 4, boron has 5, carbon has 6, all the way over to neon, which does have 10 protons all total. So, well, what does that mean? When you increase the number of protons, what does that mean? Well, the more protons there are, the stronger the attraction is to the nucleus. So, for example, lithium, let's look at a lithium atom. Lithium has 3 positive charges in the nucleus. And the more protons there are, the stronger that attraction is to the nucleus. Okay? Whereas neon, on the other hand, has 10 protons, so 10 positive charges. So the attractive force of neon is more than 3 times greater than the attractive force of the lithium nucleus because, of course, neon has more protons. So the number one reason that the ionization energy goes up as you go across the periodic table from left to right is because the number of protons increases. Okay, and I do say that down here. Okay, so as you move from left to right, the ionization energy increases, Why is that? Because of the increase, this is the fancy way to say it, the increase in the nuclear charge, which means an increase in the number of protons. Okay? So the number of protons is going up. Okay? Now, so that's one reason. Your biggest reason right there is that you're always going to say, anytime you're going across the periodic table, is there's more protons. Okay? Now you'll notice that lithium, its electrons are 1s2, so there's our 1s2 electrons, and then 2s1, so it has one electron in that second shell. Okay, where neon is 1s2, and then, so there's our first shell, basically right here. There's our first shell, and here's our second shell. And then neon has 2s2, and then also it has 2p6. They're all in the second shell. 1, 2, 3, 4, 5, 6, 7, 8, one more. Okay? So notice that lithium's valence electrons are in the second shell, and so's neon's, which means that their valence electrons, since they're in the same shell, are relatively the same distance from the nucleus. Not exactly, but relatively pretty close. Okay? So, let me summarize that again. So, neon has a greater first ionization energy than lithium because a neon atom has more protons. So, the attractive force of the nucleus is stronger in neon, and because both atoms' valence electrons are found in the same shell. Okay, and by that I mean lithium's valence electrons are in the second shell, and so are neon's valence electrons are in the second shell. Okay, if the valence electrons are in the same shell, then the more important factor here, again, is the protons, is that 3 times more attractive force of the nucleus that neon has than lithium does. So, look at the things I underline here. From left to right, the first ionization energy increases. Why? Because the increase in the number of protons, and again, I don't care how you say it. You don't have to say increase in the nuclear charge. You can say neon has more protons, and I know what you mean. Okay, and their valence electrons all occupy, or all of their valence electrons are found in the same shell. Okay, that means with more protons, the attraction to the nucleus is stronger, and since the valence electrons are in the same shell, the number of those inner shell electrons is constant. Okay? And don't worry about this. This is just a relationship between the protons and the valence electrons. It's called the effective nuclear charge. It is, again, it's the relationship between the number of protons and the number of inner shell electrons. But again, this is the key here. The increase in the number of protons and the fact that the valence electrons are found in the same shell. You say that, you're going to get an absolute perfect score. Okay? So, example number 1. Fluorine has a first ionization energy of 1,681. Oxygen's is 1,314. Explain in terms of atomic structure. Okay, here's where I want you to be really careful. Okay, I'm telling you the answer. I'm telling you that fluorine is higher than oxygen. What you can't say, because it's not correct, because I want you to explain it in terms of atomic structure, which means that's the structure of the atom. So what you can't say is fluorine's farther to the right on the periodic table, so its first ionization energy is greater. Okay, you're going to get a 0 for that. Okay, you have to talk about the structure of the atom. And again, guys, there's no perfect way to say it. There's lots and lots of great ways to say it that will get you all of the points that show that you understand. Okay, so here's some possible answers. F has a larger first ionization energy than oxygen because a fluorine atom, and I'm going to underline the important parts. Fluorine has more protons than oxygen. Okay, don't say it. Fluorine has a larger first ionization than oxygen because it has more protons. What's the it? Is it the fluorine or the oxygen? Notice I'm very clear. It's the fluorine that has more protons. Okay, and so there's a greater attraction to the nucleus. And since oxygen and fluorine both have the same number of inner shell electrons, since their valence electrons are found in the same shell, that means their inner shell electrons are the same. Okay, they both only have those 2 inner shell electrons. Okay, Another way you could say it, a much shorter way. Fluorine has more protons than oxygen. Again, what am I looking for? Fluorine has more protons. And the electrons being removed both come from the second shell. So electrons come from the second shell. That's what I'm looking for in the answer. Okay, next answer. Since fluorine has a greater nuclear charge, so fluorine, greater nuclear charge, valence electrons are found in the same shell. Boom, done. The attraction is greater in fluorine, so fluorine has a greater first ionization energy. Okay, notice in every single one of them, the parts that I'm looking for has something to do with the fact that fluorine has more protons, but that either the inner shell electrons are the same, the valence electrons are found in the same shell, the valence electrons are in the second shell. Okay, every single answer is a comparison to the number of protons and the number of electrons in the atom. Okay, so example 2. And here's my you cannot use position on the periodic table. Okay, you can't say something's farther to the right. You can say that, but then you have to then talk about protons and electrons after that. But if you just talk about that, that's not enough. Okay, so what has a higher first ionization energy? Sulfur or silicon? So I look at the periodic table. In my mind, I think, oh, sulfur's farther to the right. So which one has a higher first ionization energy? Absolutely sulfur. Okay, and then I have to explain. Okay, and again, I'm going to try to write it as simply as I can. Okay, sulfur, because B/C, sulfur has more protons than Si. So the attraction to the nucleus is stronger in sulfur. And both atoms' valence electrons, and I'm looking at the periodic table again, are in the third shell, or the same shell, something like that. Okay, and again, so what am I looking for in my answer? That right there. Okay, and that the valence electrons are in the same shell. Okay, as you go down the periodic table, this one I'm really only looking for one thing. Okay, as you go down the periodic table, as you go down the periodic table, ionization energy goes down. Okay, so remember, as you go across the periodic table from left to right, ionization energy goes up. Okay, and as you go down the periodic table, that's a little bit better, ionization, IE goes down. Okay? Now, why? Basically, because remember, as you go across the periodic table, you're staying in the same shell. But as you go down the periodic table, you're adding more electron shells that are farther away from the nucleus. And that decreases the attractive force. Okay? So, as you go down the periodic table, the number of electron shells are increasing that are farther away from the nucleus, which decreases the attractive force. That's what I'm looking for. Okay, and again, lots of different ways you can say it. So let's take a look at this. So what has a higher first ionization energy, sulfur or selenium? So again, I look at the periodic table. I see that selenium is right below sulfur. So one of the ways I could answer this is I could say that selenium is sulfur. Sulfur has a greater first ionization energy because sulfur's valence electrons are only in the third shell. Selenium's, again, looking at the periodic table, are in the fourth shell. And the fourth shell is farther away from the nucleus. So again, sulfur's valence electrons, third shell, selenium's fourth shell, which is farther away from the nucleus and not as attracted to the nucleus. Okay? And sometimes, I do use this word core electrons. That's the same thing as inner shell. I kind of use those terms interchangeably. So there's the valence electrons, the ones in the very last shell, and then there's the inner shell, or what we call the core electrons. So any electron from the nucleus out to the valence electrons is a core or an inner shell electron. Okay, so example 4. List the following atoms in order of increasing ionization energy and explain your reasoning based on atomic structure. Okay, and absolutely, here's a table right here. We know the answers, okay? We can see them. So we've got fluorine, so here, oxygen, here, tellurium, way down here, and iodine. So they say, list the atoms in order of increasing. So that means start with the smallest and go to the biggest, small to large. So which of those is going to have the smallest ionization energy? Again, remember, as you go to the right, ionization energy goes up. So if you go to the left, what does ionization energy do? It goes down. So the one that's farthest to the left and the farthest down is going to have the lowest ionization energy. So which of those is the farthest to the left and the farthest down? Certainly tellurium. And look at the numbers. Our numbers support that answer. So tellurium would have the smallest ionization energy. Okay. And now we go a little bit to the right, but we're still way down the periodic table. So iodine would be next. So iodine has a greater first ionization energy than tellurium. And then we go up to oxygen and fluorine. Again, fluorine's farther to the right, so it has the greater ionization energy. So oxygen would be next, and then fluorine would be last. Okay? And then again, if we were to explain it, we would say that fluorine is the highest because it has its electrons, its valence electrons are closest to the nucleus, and it has more protons than oxygen. And tellurium and iodine are much, much lower because they have more electron shells that are farther away from the nucleus, which reduces their ionization energies. Okay, that's a really, really good table there to see that clearly, if you just want to focus on patterns, the top right have the highest ionization energies, the bottom left have the lowest ionization energies. So as you go this way, diagonally up the periodic table, ionization energy goes up. Okay? All right, and then tomorrow we will talk about using kind of the same idea, what are called atomic and ionic radii.